Greetings, everyone. Last time we talked about gravitational forces and what the equation really looks like when you are far away from Earth. Now we're going to talk about gravitational potential energy using the same corrections. We're going to talk about dropping a ball from the International Space Station and letting it land on the Earth. We're going to discuss escape velocity, and we're going to go back and look at orbital velocity. Previously, we learned that the equation for gravitational potential energy is UG is equal to mgh. Well, that's a really good approximation as long as you're very close to the surface of the Earth. If you are going very far from the surface of the Earth, you need to use this new equation. UG is equal to negative g 6.67 times 10 to the negative 11 times m1 times m2. One of these is the mass of the planet or star or black hole or galaxy or asteroid or whatever it is that you're orbiting. And the other thing is the mass that you are finding the gravitational potential energy of. So the space station, the ball that you're throwing up into the air, whatever it is, that's the other one. Divided by the distance between their centers, not squared. Notice there is no square there. Unlike the equation for the force of gravity. This looks very, very similar to the equation for the force of gravity, except force of gravity does not have a negative, and force of gravity does have a squared there. Now, questions for you. Where in the universe is the gravitational potential energy equal to 0 according to this equation? When we're using this equation, we could kind of set 0 to be wherever we wanted. We could define a height to be 0. Well, that's not going to be true here, and I want you to determine where in the universe gravitational potential energy is equal to 0. All right, I also want you to determine what sign does the gravitational potential energy have at Earth's surface? Is it positive, negative, 0? What is it at the surface of the Earth? Okay, well, where is UG equal to 0? According to this equation, it's equal to 0 at infinity. Only when r is equal to infinity would you get that this is equal to 0. Plug in infinity for r, and something over infinity, well, it's 0. A mathematician would yell at me for saying that, but I don't care. So yeah, when you get to infinitely far away from the Earth or the Sun or whatever it is that you're testing the gravitational potential energy with respect to, you get infinitely far away, then you get 0 gravitational potential energy. What sign does gravitational potential have at the Earth's surface? Well, let's plug in 6371,000. 6371 is the radius of Earth in kilometers. Add some zeros to make it meters. You have a positive number times a positive number times a positive number divided by a positive number, negative sign. Gravitational potential energy has a negative sign on the surface of the Earth. In fact, if you are anywhere other than infinity far away, then you're going to get a negative gravitational potential. If you are less than infinity away from an object, you've got negative gravitational potential. If you are infinitely far away from a gravitating object, then you can have 0 gravitational potential energy. You'll never have positive gravitational potential. It will always be negative, or if you're infinitely far away, it will be 0. Here's a good practice problem for that. Let's say that you are an astronaut on the International Space Station, 405 kilometers above the surface of the Earth. You drop a ball from the space station. Let's assume that the ISS is not moving somehow. This isn't very realistic, but let's just say that the ISS is just hovering there somehow, and you drop a ball just straight down, I want you to find the speed of that ball dropped from the ISS when it hits the ground 405 kilometers down. There are two ways of doing this, and we're going to look at the new way first, using our new equations. Well, this is an energy problem. Delta E is equal to 0. Delta E is not equal to, well, it's always equal to W, but W here is equal to 0 because there's no external work being done on it. So delta E is equal to 0. Energy initial is equal to energy final. Okay, think for a second. What kinds of energy should we include at the beginning of the problem, and what kinds of energy should we include at the end of the problem? We've got gravitational potential, we've got kinetic, we've got spring, we've got anything else that you want, rotational. What kinds of energy should we be including? Well, I said that assume that the ISS is not moving, so think about that as well. Okay, I propose that we include initial gravitational potential, final kinetic, and final gravitational potential. Why did I not include initial kinetic? Yeah, because the ISS is not moving and you're dropping it from the ISS. Well, why didn't I include rotational? Same thing, nothing's rotating. Why didn't I include spring? Well, there's no springs here. Okay, gravitational potential energy initially. Is this going to be 0? Is it going to be positive? Is it going to be negative? Remember, anything that isn't at infinity is negative, and the space station is not at infinity. So it's going to exist, it's going to be negative. Okay, equals kinetic energy final. We're kind of looking for this. We're looking for the velocity at least. Plus the gravitational potential energy final. Again, at the surface of the Earth, that is not at r is equal to infinity. Therefore, it's going to be negative. It's always negative or 0. We have to include both. We can plug in the equations. Never ever forget the negative sign when you are using this kind of gravitational potential energy. That negative sign is very, very important here. Negative g m1 m2 over radius ISS is equal to 1/2 m2. I guess I'm using m2 as being the ball, the mass of the ball that's being dropped, times v squared minus g m1 m2 over re. That's the radius of the Earth. Well, what is something that we can cancel out? Yeah, we can cancel out the m2's everywhere. The mass of the ball is not going to affect how fast it's falling. That's good. What is RISS? Can you give me a number? Yeah, it's going to be 405 kilometers plus 6,371 kilometers, because that is the diameter of the Earth together. 405 plus 6,371, and then of course times 1,000 to get it into meters instead. Okay, equals 1/2 m2 v2 blah blah blah. Okay, re, that's the radius of the Earth, and that's just 6,371 kilometers. Convert that to meters, 6,371,000 meters. Well, rather than boring you with calculating all this out, I just calculated it myself. Got mass of the ball, radius for where the ISS is. That should be in meters. Final velocity of the ball when it hits the surface of the Earth should be 2.7 kilometers per second, 2,733 meters per second. That's quite fast. That's very fast. That's neat. Okay. Let's do this all again using our old equation, our old way of solving this kind of problem. Delta E is equal to 0. Again, there's no work being done from outside. Energy initial is equal to energy final. What do you think the initial energy and final energies will be in the old way using MGH? Yeah, we just need to have Initial gravitational potential energy is equal to final kinetic energy. There's no kinetic energy at the beginning, and we can define h equals 0 to be the surface of the Earth. If you define h equals 0 to be the surface of the Earth, you end with no gravitational potential energy, and so you don't have a UG final right there. That stands in contrast to what we did over here, where we do not have a choice on where to set the 0 gravitational potential energy. The equation itself tells us that something only has 0 gravitational potential energy when it is at a distance of infinity. Therefore, if something isn't at infinity, we have to include gravitational potential energy there and there. Neither of these places are infinity, therefore we have to include gravitational potential at both places. Keep that in mind. When you do problems like this, you always have to include gravitational potential energy unless something is going to infinity. If you are dealing with things off of the surface of the Earth, far off the surface of the Earth. However, old way of doing things where we didn't even care about any of that, we just use MGH. Well, we can set h equal to 0 to be wherever we want. Here we're constrained that we have to have 0 energy at infinity. Well, you plug in the numbers, mgh is equal to 1/2 mv squared, and you solve, and you find that the final velocity of the ball will be 2,817 meters per second. Interestingly, that's just 3% off this. Our old equation got us pretty good, actually. We were only 3% off doing it really for real. This takes a whole lot more effort than this. This is quite a bit of plugging things into the calculator. This, not nearly as much. This is far, far more accurate than this. But when this is only 3% off, a lot of people just don't care. The reason that we started off using this kind of thing instead of using the real true equation is using the real true equation doesn't really get you that much closer to the real answer when you're near the surface of the Earth. And this is looking at the space station. This is all the way up at the space station. And our old simple equation was only 3% off, even when looking at something so high up as the space station. Well, anything near the surface of the Earth, anything within the atmosphere, you can just use the old equation. mgh is equal to 1/2 mv squared. If you're within the atmosphere, you're only going to be like 1% off or less. So once you leave the atmosphere, you should probably use the new equation. But yeah, inside the atmosphere, just use this. It's fine. There's an interesting concept called escape velocity. A lot of you will probably use this actually legitimately in your work. If you go work for a rocket company or space kind of program anywhere, you'll probably use escape velocity at some point. So it's neat to examine that. The escape velocity is the velocity on the surface of a planet, or actually in orbit, which will get you to r is equal to infinity eventually. What velocity would you need to have starting at the surface of the Earth to get to infinitely far away? How much energy do you need to overcome gravity to escape the gravity of the Earth? One way of thinking about this is that according to our gravitational potential energy equation, our new one, we are always in debt, gravitational potential energy-wise. Unless we are at r is equal to infinity, we are in debt to gravity. How much energy, how much speed do we need to get out of debt to gravity? How much speed do we need to break free of Earth's gravitational potential? Well, we can calculate that now. This is a conservation of energy equation. What velocity do we need to get infinitely far away? That's like asking what velocity we need to throw a ball 15 meters up in the air, except we're just going to infinity in this case. Now, think about this. Using our old equation, UG is equal to mgh, how much energy would you need to go infinitely far away? Well, to go infinitely far away, you'd need an infinite height, and so you'd need an infinite amount of energy. How much energy do you need to pay off our gravitational potential energy debt with our new equation? Well, is that going to be infinite? Remember, we're in debt when we're on the surface of the Earth, but when we are at infinity, we are no longer in debt, we just break even. So it shouldn't require an infinite amount of energy to get infinitely far away. It would still take an infinite amount of time, of course, but just not an infinite amount of energy to do it. Well, we've got gravitational potential energy initially plus kinetic energy initially is equal to gravitational potential final plus kinetic energy final. Are any of these equal to 0? Well, when we are on the surface of the Earth, is this equal to 0? Using our new equation, I'll bring that back. Using this equation, is it equal to 0 on the surface of the Earth? No, it's not. With our new equation, surface of the Earth, that's a positive number, positive number, positive number, positive number, negative sign. We've got a negative amount of gravitational potential on the surface of the Earth. We can't get rid of this. We've got to leave it there. Okay, plus kinetic energy initial. Well, we're looking for the velocity you need to be going at when you're on the surface of a planet to get you infinitely far away. So yeah, okay, we need this because we're really solving for that initial velocity. Okay, equal to gravitational potential energy final. What is our gravitational potential energy final when we're infinitely far away? Plug in infinity there. You get negative, positive, positive, positive over infinity. Well, that goes to 0. So this is actually 0. Okay, what is the kinetic energy infinitely far away? Really, I should be asking what is the minimum kinetic energy infinitely far away, because this should really be read as the minimum velocity that you need on the surface of a planet to get you to r is equal to infinity eventually. So what is the minimum kinetic energy that you need once you are already at r is equal to infinity? Well, just like questions about throwing a ball up into the air, how much speed do you need to throw it up into the air a certain height? Well, it goes to 0 speed at that height because it has to turn around, I guess, at that height. And so kinetic energy final should also be 0. So this whole side should end up being 0. Then we can just plug in our equations. Negative g m1 m2 over r plus 1/2 m2 v squared is equal to 0. I'm using m2 being the mass of the object that we are considering. We can then solve that. We can, oh, actually, what did I do here? Can anyone see what I did here? Yeah, I just moved this thing, I added this thing to both sides, and I also got rid of a mass along the way. What is this mass? Does anyone know what that mass is? Yeah, that's the mass of the Earth. Or, more generally, it's the mass of whatever you're trying to escape. And what is this r? Well, that's the radius of the planet that you're on. Or it could be the radius of the orbit that you are in. Generally, when we launch a space probe to the depths of space, we don't launch it at full velocity from the surface of the Earth. We let it get into orbit, and it orbits around for a little bit, and then we launch it all the way out to wherever it's going. So if that orbit is a very, very high up orbit, then we need a little bit less energy to get ourselves out of the solar system or out of Earth's gravitational well or whatever. So this could be just how far you are from the center of the planet or the star or whatever that you're dealing with, that you're trying to escape. So mass of the object you're trying to escape, distance you are from the object you're trying to escape. You can then do the algebra on that, and you find that the escape velocity is equal to the square root of 2 times the gravitational constant, 6.67 times 10 to the negative 11. I'll give you all these constants. You don't need to memorize them. times the mass, that's the mass of the planet. So for Earth, it's 5.97 times 10 to the 24 kilograms, divided by r, so radius of whatever object that you're dealing with, 6,371 kilometers, so multiply that by 1,000 because we need everything in meters for the Earth. What does that get us for the escape velocity of the Earth? Well, we find the escape velocity of the Earth is 11.18 kilometers per second. 11 kilometers per second. That's a whole lot. That's really, really fast. That's why it's so difficult to get things off of Earth. There's another related concept called orbital velocity. That's the velocity that you need to be in a stable orbit around a planet or a star or whatever. This is not an energy problem. This is actually a force problem. Last time we looked at how the acceleration due to gravity is gm over r squared. And we also looked at how, very much previously, many times ago, many lessons ago, we looked at the centripetal acceleration being v squared over r. And when you are in orbit of a planet, all of the acceleration on you is because of gravity, and it's all pointed inward. And so the gravitational acceleration is also the centripetal acceleration. And so because this is equal to this, then this is equal to this by the transitive property. Well, we can just set those two equal to each other. And if we want to solve for the velocity that you need to be in orbit, we can do that very quickly. We get the orbital velocity being square root of gm over r. Orbital velocity is the square root of gm over r. G, Newton's gravitational constant, 6.67 times 10 to the negative 11. M, the mass of the Earth, 5.97 times 10 to the 24 kilograms. R, that is the radius, the distance from the center of the Earth to wherever you are trying to orbit. If you're trying to orbit just a few kilometers off the surface of the Earth, then you'd plug in just a few kilometers plus 6,371 kilometers, because that's the radius of the Earth, and then, of course, get it into meters. If you are trying to orbit something at geosynchronous, then you'd plug in the radius of geosynchronous orbit. Not the height to the surface of the Earth, of course, but the distance to the center of the Earth in all these cases. You always want to be making it to the center of the Earth. And that'll get you your orbital velocity. Interestingly, that means that the farther you are from the Earth, the slower your orbit can be, and you'll still be in orbit. The orbits that are the fastest are the ones that are closest to the gravitating body, and orbits that are far away are a lot slower the farther out you go. Notice that this is very similar to the escape velocity. The escape velocity is square root 2 gm over r. The only difference is the square root of 2 in here. The difference between the orbital velocity and the escape velocity is the square root of 2, which is 1.41. Meaning, to get to escape velocity, you just need to be going 41% faster than orbital velocity. If you're in orbit, you just need to be going 41% faster, and you will escape whatever you're orbiting. Robert A. Heinlein, who I bet a lot of you have read some of his books, he once said, once you're in orbit, you're halfway to anywhere. And that's actually very, very accurate. You're actually almost entirely there, because you just need to boost yourself by 41% to get yourself to escape velocity. Once you're in orbit, you're actually more than halfway to anywhere.